We're going to go ahead and get started today. First, I would like to thank you for joining us today. This is the fourth and final webinar in our little mini-series that we have been doing on high-purity water treatment. Quickly, while last-minute people are getting warmed up, for those of you that know nothing about Yokogawa, I wanted to go do a quick overview on us. My name is Sherilyn Marlowe. I'm the Liquid Product Manager here for Yokogawa. Philosophy as a company and individually, our goal is to contribute to society through brand-changing activities in areas of measurement, control, and information. Individually, we aim to combine good citizenship with courage and innovation. We operate in 33 countries throughout 85 different companies. In the North American territory, we have 4 head offices, one in Calgary, one in New Georgia, just south of Atlanta, one in Sugar Land, Texas, and one in Mexico City, Mexico. Just the U.S. alone, we have sales offices spread throughout, so local support is in your backyard. Anything from control safety systems to field instruments, your pressure, your flow transmitters, your handheld devices, to data acquisition. There's analytical, your GC, zircon, oxygen, TDLS, gas density, liquidizers, pH, conductivity, dissolved oxygen. We also have a system integration group called Measurementation that makes analyzer shelters as well as just skids. Semiconductor division. We have measurement division. The handheld division for like loop indicators and whatnot. We life science and related products. So again, I want to thank you for your time today, and I want to introduce our guest speaker for today's event. His name is David Paul. He is the president of David H. Paul, which is a high-tech water treatment training consulting firm located in the U.S. David has over 37 years of experience in membrane and high-purity water treatment, over 26 years of training and consulting in these areas. Give 1 second, ladies and gentlemen. We're having some audio feedback. Taken care of. Sorry about that, but he trained and consulted at hundreds of plants around the world. He has published over 160 technical articles in newspaper and papers, and he holds a BS degree in biology and an MS degree in microbiology. So I want to go ahead and pass the ball over to our guest speaker today so we can get this presentation started. I did forget to mention that we will have a Q&A section at the last little bit. The other presentations have run over the time, but this time we're going to have to stick to the 3 o'clock time period. So any questions that we do not answer before then, we will contact you directly. So thank you, David, for being here and talking to us today.
Thanks, Sherilyn, and thanks everybody for attending. As Sherilyn mentioned, this is the 4th and last one where we are talking about high purity water. And hold on, I didn't go to the very top. So if you don't know about David H. Paul, Inc., we have been in high-tech water treatment since 1988, and not just in reverse osmosis, but many, many different technologies. We have lots of different types of training, and as or we also do consulting. So if you have a problem, then we'd be happy to help you out with that. So this is the 4th 4 webinars. So we started with an overview, then we looked at, they had different names to them, but monitoring RO units was the main focus, and then the third one, monitoring RO pretreatment. And today it's looking downstream of the RO unit, and particularly just how important it is to ensure that your primary RO unit, your pass RO units are operating just excellently, because you'll have few problems downstream ordinarily if we can make sure that the RO units are operating well. So look at high purity water treatment, just very briefly again, bring everybody up to speed. A little bit on RO treat, but then the main point of today's webinar is going to be monitoring the RO unit at the downstream equipment will be operating well. So we'll look at what we need to monitor. So just kind of an overview from the first session, and just to make sure that we have the terminology down. Heavy water treatment is simply taking a raw water, that could be municipal drinking water, to a lake water, and taking it up to high purity water. We call it end use because every city will have different end use requirements. So high purity water for one industry does not equal high purity water for another industry. Well, in today's world, you almost always, you can just about say always, have an RO step between raw water and end use. This is the technology that's going to remove more contaminants, dissolved and suspended contaminants, than anything else. But have to protect it from saline, fouling, and chemical attack. So we have to put equipment in front of the RO unit to protect the RO unit from scaling, fouling, and chemical attack. We call that treatment. Orally, the water that goes through the RO membrane, called permeate, does not meet end-use specifications, so they have to polish the RO permeate up to the specifications of the use requirements. As an example, here we have an RO treatment step between drinking water as the raw water, and the end-use water here for pharmaceutical or biotech would be water for injection or purified water. So we looked at pre-treatment, and pre-treatment for biofarm type systems is different than you see in a lot of other industrial applications. So we see here softener, activated carbon, UV. This won't be as common in other industries. And then downstream, we're seeing electrodeionization and multi-effect still, and you basically only see the stills on the side. You only see the stills in the biofarm applications. And looking at power generation, we see that the treatment to protect the RO unit from scaling, fouling, and chemical attack is totally different than what we saw before. But for high purity water, we have a mixed bed ion exchange. Well, everything downstream of the RO system is going to be impacted negatively if we allow that RO unit performance to head south on us. And then the last one is semiconductor. Here we're seeing exactly the same kind of pretreatment that we saw in power generation. Now, in this case, we actually have a double pass RO unit. So today, as I'm talking about monitoring and the importance of making sure that RO unit is operating properly, we're talking about the first pass RO unit. That first pass RO unit is operating well. Likely have few, if any, problems downstream with that second pass RO system. And downstream of the several years, I can think of maybe 3, maybe 4 times we're called on consulting, and it reminded me seeing this EDI unit where a plant says, "Oh, I've got big EDI problems. Would you come and help us fix the EDI problems?" And my answer to that is, if you have EDI problems, you have upstream RO problems. So you need to focus on the RO problems and get that fixed prior to working on the EDI system. So just keep that in mind. When you start having problems downstream, you need to take a hard look and make sure that the RO unit is not having a problem. Because we have this kind of a system we're looking at right now, where you have double pass RO, EDI, mixed bed, and a lot of other treatment steps to come. Use water may be fine. The price, these other technologies are polishing up the problems that a poor performing RO unit is giving you. You're paying that price even if you're meeting end specifications. Additional treatment steps. So again, all these are going to be negatively impacted when RO unitly performing. So rule number 1, The efficient and effective downstream treatment depends on good RO unit performance. And rule number 2, efficient and effective RO treatment depends on good RO pretreatment performance. So when problems downstream, we need to look at the RO unit. When we see problems with the RO unit, we ought to look upstream. We have pretreatment issues that are not protecting the RO unit from saline, fouling, and chemical attack. So it's probably one of the most important things, and over some of this second webinar, which is available online. So you can go to Yokogawa and view that if you didn't get a chance to see the second webinar. They're looking at how RO membranes reject dissolved and suspended contaminants, and that we have charged and uncharged contaminants under dissolved and living and non-living. This is important to remember. Something that has a charge, we call those ions. Ions are very well rejected. We see that the more charges an ion has, the better it's rejected. Other things, though, have to reject it based on size alone. So gases like CO2, oxygen, nitrogen, and sulfide, your normal gases that could be dissolved in water, they basically go through the membrane, not rejected at all. Whether other uncharged things go through the membrane will depend on the molecular weight. So we can molecular weight, the MW, below 20 Daltons or 20 molecular weight. Then we have rejection, and then as you get bigger and bigger molecules, you get better and better rejection. And finally, because suspended particles are all relatively huge compared to dissolved, they're going to be nearly 100%. It's just going to be, little imperfections in the membrane that will allow a few viruses to go through, like 1 in every 10,000 viruses might make it through, but maybe 100%. So if we summarize this, the thing to remember is suspended particles are almost 100%. So super great rejection. Dissolved substances, 98, 99, 99.8. Great rejection of things. Our issue is going to be uncharged. And TC, total organic carbon, total oxidizable carbon, those compounds are uncharged. So it depends upon size. If they're huge, all right, they're going to be rejected well. But if they're tiny, they're going to go through that membrane. This is for silica. So there are many uncharged compounds. So in water, there's going to be a different amount of silica that will go through the membrane. And gases, 0. So with organics, that basically any compound has a carbon atom in it. The symbol is C, except the P-life forms are carbon. Things that came directly from carbon dioxide, like carbonic acid, bicarbonate ion, and P forms of carbon, like graphite, diamond, activated carbon. So basically, anything else besides those are going to be organics. So the reason we call them organics, they basically all come from organisms and are just a lot of organic compounds. You never know. You have 5 milligrams per liter of ppm of TOC in your feed water. That could be 50,000 different compounds. We have no idea because so many organic compounds. Some industries, organics can be a problem, and some not so much. So some industries worry about TOC, others don't. But the thing I want you to remember about organic compounds, some of them can directly foul membranes and ion exchange resin, directly meaning they bond directly to the membrane. So oil or cationic polymer can bond right to the membrane. But the thing that is really, really important for everyone to realize is that organic compounds are for bacteria. At least certain organic compounds are. So that TOC that passes through the membrane is uncharged, and it's going to be small, and it's likely that many of these organic compounds are going to be food sources for bacteria downstream. So the big part of this discussion is that if the RO membrane is not rejecting well, if it's performing poorly, then organics are going to go through the membrane more. So we measure organic compounds with TOC. Here are a couple of different T. Silica is another one where many of the silica compounds are uncharged, so if they're relatively small, they can pass through the membrane. In industries, silica can cause a problem. Other industries, not so much. Silica can always scale an RO membrane system if the silica from like a well water is too high. We make a silica analyzer, either enter on stream, and here's just a couple of pictures of and type analyzer. Important contaminant downstream of your RO membrane system is going to be CO2. And that's because of what the next few slides that we're going to see. It's a scale with pH at the bottom and 0 to 100% on the left side. And we see that CO2, when it dissolves in water, if the pH is below about 5, easily all of your CO2 is in dissolved CO2 form. Another name for dissolved CO2 is carbonic acid. But never completely goes away. So at certain levels, we'll have milligrams per liter parts per million, and then as the pH goes up and up, we just get smaller and smaller quantities, but we'll also have some CO2. It's just pretty insignificant once you get into higher pH. Well, CO2 turns into, at pH, is bicarbonate ion. Now remember, membranes reject charged things really, really well, and the more charges, the better it's rejected. So 2 is the gas. CO2 is not rejected by an RO membrane. Bicarbonate ion is, and it's rejected well. It could be 98%. But we get out at normal range in raw water. So our raw waters are going to be in the 7 to 8 range. Seawater is going to be the 8.5 range. So most of the CO2 in water that into a plant is in the bicarbonate ion form. As the pH goes up, that the bicarbonate starts disappearing, turns into carbonate -2. So this is even better rejected. You know, we have the carbonate even at a pH of 5 or 4, just in very, very small quantities. But by the time you get into 7 to 8 range, then we have to worry about it scaling in RO unit. We talked about that in the last webinar, so we won't go over that here. So when you put those 3 graphs together, this is what you get. So dissolved CO2 or carbonic acid is at the lower pH range, but in normal operating range of an RO unit, most of your CO2 is going to be in the bicarbonate ion, but you have also carbon ion. So if we only are looking at CO2, because there's always a significant amount of CO2 in the feed waters, we see CO2 is not rejected by the RO membrane. We talked in the last, in the treatment webinar, we talked about potential RO problems of scaling, fouling, and chemical attack. We did not talk about other problems like ozone leaks, mechanical damage, where maybe particles have cut a membrane. One saw a hydro pump impeller blew up and cut the lead membrane with charge from the impeller. So anything that would damage the membrane would cause more contaminants to go through the membrane. So anything that is going to reduce the performance of the RO membrane rejection is going to put more contaminants downstream. That's going to impact downstream of your purity treatment steps. So RO problems, you're going to get more TOC, more organics going through, more CO2 going through. Valent, that means single charged ions, and more divalent ions. So this is something maybe to keep in mind, that membrane gets, if it's damaged, like chlorine attack, if it's damaged, at a certain point, it will let the monovalents through, but the divalents are still very well rejected. And as more damage occurs, the divalents start going through it all. So if we catch problems at an early stage, that's going to be the best for us. Okay, now let's talk about the potential consequences of bad RO unit performance. So in this case, we see the RO box is red, so the RO unit has got problems, either scaling, fouling, chemical attack, O-ring leak, permeate back pressure damage, anything that could cause that membrane to not reject feed water contaminants, is then going to allow more contaminants to go through the RO membrane. It's going to happen downstream. Well, your TOC going through, and TOC then over time can biofoul in a tank. I was at a power plant, this is 4 years ago. About, I can't remember exactly, I think it was 3 years, it could have been 5 years. For huge, this is like a 1 million gallon tank. This huge tank to biofouled, and the way that we found it is that the mixed bed with shortened run times and really long rinse up times. That's kind of the indicator for organic fouling. So ion exchange membranes were becoming organically fouled. When there's this problem, then you get called in to say I have a mixed bed problem. But then you start looking, and as I said, I'm always going to look upstream, find out that this RO unit is not operating well. It's putting in more TOC, which is eating bacteria. After 3, 4, 5 years, when you open this up, there's actually biofilm. There's actually slick biofilm on the surface of this huge tank. So the fix here was, had to remove the organics from this, do some aggressive cleanings, regens, and then clean out this tank and get the RO membrane system fixed. So as the RO membrane is passing more, not just CO2, because we know that CO2 is going to be totally rejected, but if damaged, then it's going to be allowing bicarbonate ions and even carbonate ions to go through the membrane. And when it's the degasifier, because of the pH, we're going to have more CO, but we're also, since we've got ions going through here that aren't going to be degassed, then the ion exchange bed has to pick them up. And it means the runtime of the mixed bed ion exchange unit is going to be shortened. So there's going to be more regenerations and maybe even eventually a reduction in quality. And as we're passing TOC, everything downstream is going to have more bacteria. I'm going to use the term biofouling here. And it's just basically we should think of increased bacterial numbers. When you're seeing, especially when you get into a double pass RO system, you're not going to see clinging, hanging, slimy biofilm on the pipes. There's not going to be that much food. But you're going to see your bio numbers worse. Same thing, like I said, for the mix. So that RO unit performance drop has an impact downstream. And the pharmaceutical, in this case, got an EDI unit, so it's allowing CO2 or more ions, I should say, the bicarbonate ions, and maybe even the carbonate ions to go through, which that The EDI unit, if you want to make the same quality, you're going to have to crank up the voltage and to drive those ions across. So the worse the RO unit gets, the higher and the higher and the higher the voltage is going to become. And since you are passing bicarbonate ions and carbonate ions, due to high pH in certain areas of the EDI unit, they're going to change into carbonate, and you can get calcium carbonate scaling. And due to the TOC passing through the RO membrane, then areas that are not energized, then you get bacterial numbers, I'm calling it biofouling. So impacts, especially volatile organics, so the small organic molecules that through the RO membrane and the EDI unit, because you've got a bigger load going through, that can actually then volatilize in the still and cause problems. And semiconductor, this is where we're looking at a dust system. Gas RO is operating well, like I said, usually have few, if any, problems downstream, but it's quite commonly. We actually had 2 autopsies come in. Client sent us an element from the second pass RO unit and also from the first pass. And I looked at second pass autopsy first. I couldn't believe it. I've never seen scaled second pass RO membrane before, ever. It's the only time in all my years that I've ever seen that. And if I knew that the first pass had to be just shot into the scale of the second pass, and sure enough, when I looked at the autopsy on the first pass RO unit, it had ejections of like 50%. It was just totally shot. But because you have all this downstream equipment, nobody may be banging on your head because the end use quality is not good enough. Because all this equipment that is taking slack of that first pass RO unit's poor performance. But it does take a toll. It's going to cost money. And some of the things we've already talked about most of these, so I don't need to go over that again. But it's going to reduce the efficiency down until things are really bad that you're actually going to see it in the high purity loop, because there are so many treatment steps. But it's going to be a cost to pay that. So we want to be able to catch problems at an early stage. Now, we went over this in the RO monitoring. Permeate flow, pressure drop, or just pressure drop. Most of your manufacturers' software programs don't normalize for pressure drop, which is normalizing for temperature and flow rate. It's okay even if you just use pressure drop. We want normalized permeate flow and for sure normalized salt passage. And why? So we can make sure that the system is operating as designed and we catch problems at an early stage. So I'm not going to go into a lot of detail. We did go over this in the RO monitoring. So notice permeate flow with scaling and fouling. You'll see it trend down. So this is where we will jump on things. Right when we start seeing problems occur, to be monitoring and trying to catch these problems at an early stage. This is normalized pressure drop. Should be monitoring the pressure drop across the first stage and the second stage, and that could be with on-stream indicating transmitters. It could be you have some that just has the indicators only. But input this into software programs, performance software programs. All the membrane manufacturers have them for free, and then you monitor your performance. So when you start seeing salt passage increase, we don't wait too long before we figure out why that salt passage is increasing, because that is going to impact all of our downstream equipment. Salt passage, we compare the feed and the permeate conductivity. We're actually not looking at feed and permeate, but we see 2 channels here. We could have a feed and permeate on here and be able to track what's happening. At the software programs, for sure, we can track what's happening with the membrane performance. And then for fouling, normalized permeate flow will actually bio or particulate fouling will be actually in the first stage. So again, we want to judge this at an early stage before it starts impacting our downstream high purity systems. Being serious chemical attack almost from day one. So this could be chlorine attack, and we want to jump on. So with chemical attack, the pressure drops won't give us any information if pure attack, but passes will definitely go up. Okay, as we're monitoring downstream of the RO unit, we will monitor the permeate conductivity. We monitor TOC, silica. Now, this is for the highest purity system. Not everyone, like I said, cares about silica, but certainly everyone cares about conductivity. As permeate flow, the pressure drop across each stage so we can find out whether it's front-end fouling or rear-end scaling, and the normalized salt passage. And with on-stream instruments, and then we also have to have calibrated bench portable type instruments so that we can make sure that our on-stream instruments are accurate. Actions that we have to take when problem. This is something that hopefully is intuitively obvious now. If O-ring leaks, it's hard to imagine that there's much worse than that, because O-ring leak bypasses the membrane. So now you're talking particles can go through, double charged ions, single charged ions, really everything. A small portion of the feed water is bypassing the membrane. That is immediately going to impact downstream. So typically, you're not going to see an O-ring leak until you start up, so you may just be running fine, you shut down, you start up, and boom. And rolls, gets cut, or in some way is not sealing properly. See something like that, that's something that really needs to be jumped on. Even if it's not impacting your end use today, it's going to impact in your downstream equipment. Fouling, biofouling being the common, again, initially, downstream equipment is going to save you, but eventually it's going to be a nightmare. So that could be chemical cleaning. With the scaling, we don't scales to say there because scales conductivity in the permeate, and also the starting and stopping of RO units with scale crystals on membrane can cut the membrane. So crystals can be sharp. So fouling, scaling, and chemical attack, which in a lot of cases means that you have to look at the pretreatment system and do the things that we talked about in a previous webinar. You want to chemically clean in an early stage. This is a big problem in the industry. We wait too long. So we want to clean, and we're hoping that it won't get any worse. But an early stage to try to keep that conductivity, keep the TOC, keep the silica down to new or near new performance. And then if we see damage, we can replace the damaged elements. Doesn't mean you have to replace every element. It's the ones that can get you back to good performance. To summarize and conclude, so for treatment monitoring, where each industry will have their specification. So micronics rinse water have on-stream instruments that are measuring parts per billion levels, parts per trillion levels of all the different contaminants. For power stream, maybe specific conductivity and TOC is not as common, but certainly silica. But everybody's going to be doing conductivity or resistivity. Resistivity is undivided by the conductivity, so it's just a different way of measuring basically the same thing. Some industries measuring TOC, some industries measuring silica, all industries monitoring normalized permeate flow, pressure drops, and normal up passage, and that we correct problems at an early stage. In the RO unit, and then if the RO unit is having a problem, take a look at RO pretreatment. Once we fix those problems, then we'll see if there's a continued problem in the post-treatment system. These webinars are just, usually 45 minutes long. So if you want more in-depth training, we have lots and lots of training. Some of the upcoming that we have, actually this is next week in Albuquerque, New Mexico. We have 3 days on high purity water, and then a month on optimal design and operation. And just about every week somewhere around the U.S. we have hands-on training, filtration control, monitoring, and maintenance of RO systems. So if you want more in-depth understanding than what you can get in the webinars, please give us a call, and also for your instrumentation, Yokogawa, a call. So now we'll turn this over, and Shirley will be asking questions.
Thank you. You could please pass the presenter ball to me. Great. Thank you for hosting today. And ladies and gentlemen, go ahead and answer. Type your questions in the Q&A section if you have them. And like I said, this was recorded, so you see a follow-up email in the next 24 to 48 hours that will have the link to the recording of it, and then you can always contact us. Real quickly, look at this one as well, so you have our contact information. We will start to read so sorry about this. So, David, our first question that we have is with brand new membranes. There we go. Help. Membranes ran for about 1.5 years before cleaning. It's a 2-stage unit, and the second stage permanate conductivity increased from about 75 to 110 after the cleaning. Is increase in conductivity normal after first cleaning of the membranes? A dark color was during the CPI.
Yes, it is relatively common to sensitivity increase after a cleaning. Now, if you're to be monitoring your normal permeate flow, your salt passage, and your pressure drop, you'll actually usually see that within the first, could be a week to 6 weeks, your passage will drop. You'll go up a little bit. Normalized permeate flow will drop a little bit. Your pressure probably won't do anything. But that's my understanding this is that I think that's when a layer of fouling, layer of biofilm covers up the membrane, covers up any imperfections, any areas where any particles might go. So you do a chemical clean, then you're removing the layer off of the surface, so that it's very common that you'll get a conductivity increase, but then you within the next 1 to 6 weeks, that conductivity will go back down as the layer forms again. So after cleaning, if you actually have the increase that doesn't go back, and that's a good size conductivity increase, that's 75 to 110. If it didn't come back, then since it was a second stage, it could have been a healing event where crystals actually cut the membrane, damage the membrane. But when you dissolved the scale, when you cleaned the scale off, there was down left. As far as the green color, you know, it's the second stage. If that's going to be inorganic, which I would guess, but I would also be looking at piping materials and just make sure that there wasn't something in the cleaning that could be dissolved by the cleaning solution. So I tell just by seeing this a dark green color.
Thank you very much. We have a second question here, is how can I use amines to inhibit CO2?
I don't know. Never used it. The common way of inhibiting CO2, if we're talking about the high purity water system, I'm not talking about like boiler feed water or actual boiler control. So when you're saying using amines to inhibit CO2, based on what we have talked about so far, like I say, I have no experience with that.
But those are the only questions that we have right now. We do have another couple minutes on the line here if you want to type your answers or your questions to us, and we'll answer them. Otherwise, thank you for attending. And we appreciate, for those of you that have seen our series, and you can look for, like David said, on the website. We'll also send a link out to them. You have our contact information at Yokogawa, and you have David's contact information here as well. If you send me questions, I can forward them to him. That's what we've been doing in the past. So, I want to thank you so much for doing this for Yokogawa, for us, so we can educate our customers as well. And again, thank you everybody for your time today.
And Shirley did a great job being monitor. And thanks. I actually end this one sooner because we have gone over even almost 15 minutes, I think, on one of them. So I thought I'd make this one a little bit shorter. And we didn't get quite as many questions. So you got the hook. Got a short webinar this time.
It does look like that is going to be it today. Everybody is starting to close out. So again, thank you everybody, and always feel free to email us with any questions that you have. Have a wonderful rest of your day.
Bye-bye.